Hi, welcome to Math for Designer DD211, and this week is lecture 11. We're gonna learn about two-dimensional transformation with matrix. So let's recap what we learned last time in lecture 10. So we talk about dimensions like this. For now, let's focus on just one dimension and two dimension. At first we have the world where we talk about one-dimensional object, or in this case just a number. Now you have a number, let's say 5 on a line, and it is a function like that we call transformation. That tells you how you move points on the line to a new point. Like sometimes you can simply move points along the line, like by some amount. In this case, you can describe it as this function when you add a single constant to every outer point on the line, and then the whole line will get shifted. That's one thing you can do. Another thing you can do is you can multiply a number. You can multiply every number by a single constant. In this case, you are gonna scale things up. if this number is higher than 1, or you will shrink it if the number is between 0 and 1. And you could multiply and you can scale up and flip it, like if the number is negative. There are actually 4 cases if you consider them separately. Like it could be greater than 1, could be between 0 and 1, could be between -1 and 0, and it could be less than -1. There are several cases, and for each case we describe those transformations in different words. So that's one dimension. And then we have a line segment or an interval, right? And after applying the function, calculating and computing where the new interval should be, and maybe you start from here, and after the transformation you have this kind of interval instead. So you can see that it kind of flipped and scale up at the same time. And that transformation can be described by just using a single equation. So that's the world in one dimension. Oh, and also we mentioned that this is actually related to the inequality. If you remember from a long time ago, when we try to solve for an inequality, we can also think of it as transformation of lines in one dimension. And then we move on to the two-dimensional world. So instead of just a single line, we have 2 lines or 2 axes. And then we have a point in the plane. Right, that is a coordinate of a point in this plane. And then we discuss that, okay, actually when you try to use an equation, in this case it's an equation from a vector to something else, to a new vector, then there are several ways you can accomplish that. And the first thing is it is convenient to convert from a point to a vector. And even though they look the same, there are 2 numbers and they are separated by a comma or maybe a line, and there's this parenthesis, right? They actually convey different concepts. We just sometimes convert them back and forth for convenience. And so in the plane in 2 dimension, we can transform a one-dimensional object, or in this case just a vector, by using some kind of vector operation. And then in the next step we still have the plane, the 2-dimensional plane, but now we look at how we can describe the transformation of 2-dimensional objects in that plane. So if you remember the golf activity, you have a shape and you apply a function or transformation, and that shape become a new shape somewhere on the plane. And there are several transformations you can do. There are several simple transformations you can do. You can rotate, you can dilate, or just scale up, down, or flip and then you can translate. Or just move the shape around on the plane. We describe a transformation using these keywords. Oh yeah, and some reflection. You can reflect a shape across a line or across a point. And there's several transformations. And then we can chain them up. We can do one and then another and then another and then another. And we discussed that some of these transformations can be described using just a vector notation and vector operations. Like for instance, the dilation means you simply multiply every coordinate by a constant. So if you multiply everything by 2, it means you scale everything up by a factor of 2. It's 2 times as large in both dimensions or both directions. Yeah, some of them can be described using a vector, but some can't. You can reflect around a point using a vector, but to reflect around a line, you can no longer use a vector. And the question is, what do we do? If you can't use a vector to easily compute a transformation, what are the other options? And the answer is, as you can see on the screen, right now we use matrix. So we're gonna do with matrix to describe this kind of transformation. And by the way, I believe some of you have seen or have heard about this matrix stuff already. Usually it was introduced in grade 9 or 10? Grade 10, I think. As something, some abstract idea, some abstract mathematical idea. It is an object where you can do some stuff like add, multiply, subtract, take power, do stuff. But here I want to introduce it as a tool to solve this particular problem. And see why we have to do it this way. And let's go to the topic, which is matrix. Right, and we are saying that at the end of the day, which is in section 2 and 3, we're gonna see how we can use this matrix to transform stuff. But before that, let's talk about what is the matrix in the first place. So a matrix is an ordered collection of numbers. Is already an abstract idea. Yeah, of a collection of numbers. What are they? You just have a bunch of numbers. And usually when you think about a bunch of numbers, you think of spreadsheet, right? Or some kind of, a data, a book. And you are partly correct. You can actually think of a spreadsheet as a matrix, where each entry or each cell has some kind of information. Sometimes it's a number, sometimes it's a word. It kind of works. But in this case, for math people, or for mathematical study, we think of a matrix as an ordered collection of numbers. You are free to put anything inside a matrix. You can't even put a matrix inside a matrix. Which is kind of a fun concept, I guess, but difficult. So yeah, you can usually put anything, but for now, let's imagine that it's numbers inside a matrix. And in general, you can define matrix by any size, any dimension. And you can have a matrix with 10 rows and maybe 4 rows and 5 columns. You can have numbers, you can have whatever you want. Nobody's gonna stop you. Just put numbers inside of that rectangular shape. But for the sake of this topic, which is a transformation, we're gonna focus solely on the 2x2 matrix. This can be generalized using a 3x3 matrix in case you wanna do some 3-dimensional transformation, which is actually the main topic for for computer graphics. If you want to understand what is behind the scene, and how do we know? Okay, if you stand at this point and you look at that object, which side of the object you see, and where you cast the shadow, where the light goes, all those crazy stuff. Like that's a topic for some other times. But for now, we're gonna focus on 2x2 matrix, just to give you an idea of how we can continue or generalize that to 3-dimensional or by 3x3 matrix sometimes later. So for now, just 2x2 matrix, but just keep in mind that almost everything I say here can be applied to matrix in other dimensions as well. Okay, so we have a 2x2 matrix, and is it just a collection of numbers? A, B, C, D. There are 4 numbers, and each of them are real numbers. For now, in actual application, maybe you don't need real numbers. For now, we have 4 numbers, and for the moment, we don't care yet what these numbers are. You might ask, why do we have to put the smaller one on the top left, or something? Can we put just 3 numbers and leave one of the number blank? No, you can't. For now, for a 2x2 matrix, just put 4 numbers. They could be the same, they could be different, they could be positive, they could be negative, they could be any numbers you want to. But the thing is, soon enough we will see how what each of these numbers actually means in terms of the transformation. So now we have a new object, a new mathematical object that we can play around with, which is a matrix. And at glance, you may see that it looks similar to what we just learned last week, which is a vector, because a vector has 2 components, like the top and the bottom, and then a matrix has 4 components. So you increase by you increase the shape horizontally, right? But eventually we will see that these 2 are actually the same. A vector is actually a matrix. It's just a matrix with 1 column, kind of. But yeah, they look the same. They look similar. So it's like some new object, some new tool, some new toy we can play with. And once we have numbers, a collection of numbers, then the next question is we want to ask what kind of operations we can perform. And there are 3. There are more than this one. There are 3 basic ones, and the 4th one, which is actually the most important one. It is the reason why I have to introduce the matrix notation for the study of transformations. So we can multiply given 2 matrices, A and A prime. Suppose this egg, there are egg numbers here, and a vector. So you can see that we can mix a matrix with a vector, and also a real number K. Then we can define these 4 operations. So first we have a scalar multiplication. And whenever you see some numbers in math, almost always you can imagine that we can multiply that new object, in this case that new matrix, by a number. Is it about scaling? We will find out soon. And then we can add 2 matrices together. Again, that's natural. If we have numbers, then we should be able to add 2 numbers, 2 objects together. Then we have 2 other operations which doesn't make sense at first, but we will see later that it actually makes sense to define this way. So you can multiply a matrix to a vector. Multiply a matrix, this 2x2 matrix, to this vector. And interestingly, this is exactly what we need, like to fill in the gap from last week. Like what we couldn't do last week can be done using this notation. And lastly, this is the new topic that we will learn this week, that you can multiply 2 matrices together to get a new matrix. This is a new matrix. Oh, by the way, if you multiply a matrix to a vector, you get a vector. Not sure if that makes sense, but if you multiply 2 matrices, you get a new matrix. So there are 4 basic things you can do in using matrices. So let's see how we can accomplish those things. So first we have the scalar multiplication, which is simply saying that if you multiply a matrix, but if you multiply a constant to a matrix, then you can achieve that by multiplying every single entry by that constant. So in a sense, it looks like you use the distributive property. Just like when you multiply a number to a polynomial, and you multiply everything by that number. Similarly, this is what we have. And this is a short example here. If you multiply 4 to this matrix, and you multiply 4 to every single entry, and the result is this new matrix, 4 and 0 and minus 8 and 12. And nothing fancy yet. Then we can add two matrices together. This is also still natural. If you have two matrices, this matrix A and then A prime, then we can add two matrices together using the what is that, component wise. I think that's too fancy. Component wise. So you add an entry by entry. Maybe just like if you have an Excel, and you have two Excel, then you can produce a new by using the sum or something. And this is still natural. If you have two matrices and you add them together, you would expect that we simply add the numbers in the same position together. So in this case, you add A to A prime because they are both the top left entry of the matrix, of each of their matrix, and to get A plus A prime in the top left as well. And then we repeat that for other entries. You add B to B prime, you get a new number in the top right. And you add C to C prime, you get a new number in the bottom left. And then you add D to D prime, you get a new number in the bottom right. So again, nothing fancy yet for a matrix. And this is an example, and there shouldn't be any dash. So you add that matrix to the other, then you get this as a result. 0 plus 7 is 7. 1 plus minus 6 is minus 5. 2 plus minus 5 is minus 3. And lastly, 3 plus 4 is 7. Yeah, nothing fancy yet. But now that we are going to getting some interesting result. And these are the first two operations. So the next is, what if we multiply a matrix to a vector? And this is the part where it might be confusing at first, but you will see that eventually it makes sense if we want to accomplish the transformation. So first we have a matrix on the left, and then a vector on the right. If you happen to know this already, then you would know that the way you do this is you multiply the first row to the first row of the first matrix to the first column of the second matrix. And then in this case you multiply A and B to V1 and V2, and the result is A times V1 plus B times V2. If you ignore the middle for a moment, that's the result of matrix multiplication. So not only you have to rotate stuff a little bit, you also have to kind of remember that we multiply them pointwise. So you multiply A to just V1, you multiply B to just V2, and the result is A times V1 plus B times V2. Which is kind of weird at this point. But please bear with me for a moment and we will see another way to visualize that. And also we repeat the same thing but with the second row instead. So you have C and D and then V1 and V2. You multiply them together and get the bottom row, which is this one. C1 times C1 and D times Oh, sorry, that's a typo. It should be a D. So it's D times V2. But that's the natural, usual way that you used to remember how you multiply a matrix to a vector. Right? But then another way, which not sure if it's more intuitive, but it makes sense in the context that we are going to study, is that yeah, let's take a look at the middle part. Right, so here you see that A and C and B and D are still in the corresponding position. And A is still on top, C is still in the bottom. Right, because usually when you multiply the when you multiply the row to the column, you have to rotate that by 90 degrees, and kind of think about what if which one is on top, which one is at the bottom, right? But here, like A and C and B and D are still kind of in the same orientation. A is on top, C is at the bottom, B is on top, D is at the bottom, right? But what we do is we separate V1 and V2 into two components. So we have V1 time multiply to the first column in this new notation. So if we reset everything, we have V1 times the first column, and then we have V2 times the second column, where each of these operation, we can think of it as a constant times a vector. Now this becomes a constant times a vector. And once we have that, then we can go back to the definition of this multiplication. And likewise, we have B2, which is a constant at the bottom times a vector. So in a sense, you only have to rotate this vector V1, V2 by 90 degrees. You still keep the same orientation for the first two rows of the columns of the matrix. So for instance, yeah, there's an example below here. So if we have this matrix and we have this vector, right, then we still keep the same orientation for 2 and minus 1, and the same orientation for 3 and 0. What we change is we multiply 4 to the first column, and you multiply 5 to the second column. And you do it one by one, like 4 times this vector, and you distribute 4 inside, so you get 4 times 2, which is 8, and 4 times minus 1, which is minus 4. And likewise, for the second one, we have 5 times this vector. So we have 5 times 3, which is 15, and 5 times 0, which is 0. And finally, we add them together to get 23 and minus 4. So that's how you accomplish matrix vector multiplication. And this is a special case for this class. And we study two-dimensional transformation. There are actually ways you can multiply a 3 by 3 matrix to a 1 by 3 vector, and that works too. Using similar concept. You can even multiply this kind of, let's say, matrix, which is not a square, like it has 2 rows and 3 columns, to a vector. Or that should be GHI, maybe. That works too. Or actually you can do some other stuff. But again, we are not gonna talk about the complete way you can multiply any 2 matrices. For now, we focus on this multiplication and try to explain what this actually represents. Because if you take a look at the result, it doesn't make sense, right? What is A times V1, B times V2? Right, but once we have this middle computation or middle form, right, then that makes more sense in terms of matrix transformation. So this is how you multiply a matrix to. This is how you multiply 2 by 2 matrix to a vector in 2 dimensions. And yeah, that's a motivation for that. Oh yeah, I think I kind of explained that a little bit earlier. Like if you color everything, then you can see that this V1 is used twice, V2 is used twice, and A B C D are still in this corresponding position. Right, but the question I think everyone or most people would have is that why don't we just define this multiplication by multiply a number inside as though this is a constant? It would be very nice, right? So if you multiply this matrix to this vector, then why don't we just multiply vector v to these two numbers? But do we have to multiply v1 to the first row or the first column and v2 to the second column? Of course, it is wrong, but you might have this kind of question. Or likewise, why don't we just just make it a new vector instead? So just keep v1 on the top and v2 at the bottom. That will make everything a lot easier to compute. But the answer is that because these two are let's say meaningless. Yeah, it is easy, but it is meaningless. In terms of it doesn't give you any new information about the world. It could work, but it doesn't it doesn't tell you what the result looks like. Unlike this kind of multiplication, when we will find out soon that this is actually a transformation that we are looking for. So if you have a shape or a vector, and then you multiply that vector by some matrix, then that would give you some transformation of how this vector is changed to a new vector. So there's some quick reason why we define this way, but not any other ways. And also there's kind of not a math not a math reason, right? But there's some kind of special case. It is natural in this way if you do it this way, because there's a vector. If you remember, right, there are two special vectors called the unit vector I and j. Right? And I represents a vector to the right by one step. Usually when I describe, okay, you move to the right, you move to the left, you move up, you move down. Okay, those are just words. It could be unclear somehow. But if you define it this way, then I can say, you move to the direction of I by 3 steps. You move to the opposite of j by 2 steps, for instance. So if you define this way, and you have this vector I, when the top is 1 and the bottom is 0, then if you multiply in this way, like using the notation that we just introduced, then the result would be A and C. So in this sense, like there's a special operation where if you multiply a matrix to a vector I, then the result is the first column, which is convenient in the future, as we will see sometime soon. It's convenient that if you move the vector I to a vector A and C. And likewise, I think I have it at the bottom, but let's put it in the same page, on the same page. So if you multiply the matrix to vector 0, 1, then using the formula we have A times 0 plus B times 1, C times 0 plus D times 1, which gives you B and D. So again, if you multiply this matrix by the vector J, which is the vector that points upward, then the result gives you the column, the vector that is the second column of the matrix. So in a sense, like this way of multiplication gives you two columns. That's gonna be explained at some point. And why is it important to know where the I and the J go? Okay, so that's some short question, some short reasoning. Like we will see in the future why this makes sense. So yeah, that's one way. That's for I and that's for J. Multiply a matrix to the vector J and you get just the second column. and once we have this fact or this observation, right, then you can describe the way you multiply the matrix in this way. So this vector vi and v2, right, can be broken apart into two vectors. Because remember that this vector is if this is a vector v1 v2, right, then this comes from the vector v1, the movement in the x direction on the x-axis, and then v2, which is a movement in the y-axis. So this vector can be broken into two different vectors, right? And in this form, like now it kind of makes sense to multiply the first column by the first vector, and then the second column by the second vector. And that's why you get this as a result at the end. So yeah, that's how you multiply. There's some explanation or reasoning why multiplying matrix in this way makes sense. And there's a full clip we will cover soon. And that's actually a tool that you can play with on Desmos. And so in a sense that this matrix here, which is the thing we see on the left, and sometimes it depends on your notation, but some people use circular bracket. Some people use bracket that are kind of like a rectangle. They're the same thing, but preference. So that's the first section. And actually, let me give you a quick look on these two that I mentioned in the slides. But don't forget about it. I will put a link into the YouTube as well. Oh, but also I should put it for the class first, right? Okay, that's the link. So that's the link to Desmos. Yeah. This is by the way, this is not my Desmos, is someone else. So yeah, there it is. So yeah, there are three vectors. Like we have this vector 1 1, which is the vector we want to transform, and then we have the bases, which is 1 2 and 1 0, the vector I, and 0 1, the vector j, and the vertical one. This comes from this clip on YouTube, which again you can click and watch the clip. And yeah, suppose you have a different vectors, or suppose you have a matrix, and that can be represented as a point. Then you can try to skew or move these vectors into anywhere you want to. And once you multiply this matrix here to the orange vector, then you get this transformation. It looks kind of clippy, but let's go back a little bit. And so we have this vector, and the transformation we have the vector that we need to transform, and then we have this matrix, which kind of the rule on how we transform the vector. And once we finish that, then we can animate. So that'll be the result of the multiplication. So this vector multiplied to this matrix gives you this new vector. So it gets moved somehow. And another thing you can see from the screen is that not only the orange vector moves, like these two vectors also move. And because these two vectors move, then the whole plane or the whole grid has also moved according to the position of these two vectors. We will learn this in details in the next section. But for now, just to give you an idea of why multiplication is important. Yeah, let's do it this way. Then we can take a look at, that's the original. And then we transform these two vectors to a new point. That's gonna transform this vector to a new point as well. Okay, so that's the link. Just, play around and have fun, I guess. So that's the end of the first section. So see you in the next section.